that it was on the PowerPoint slides, and all you had to do was look at the PowerPoint slides, and the answer was on the PowerPoint slides. You just had to write it down. So everybody should have gotten that right. When we go through and do a neutralization reaction, it's the same thing as a double replacement. We'll exchange the hydrogen for the potassium. We'll form H2O, or also written as HOH. Both are fine. Okay. And K2SO4. Why is the phase on H2O liquid and not aqueous? Water doesn't dissolve in water? Yeah, it doesn't really make any sense to say water dissolves in water. That's why we refer to it as its standard phase, liquid. Okay? So just be kind of aware of that. The other one that was challenging was the combustion reaction, which was very, very, very difficult. Well, at least I think it's very, very difficult. And I wish I had spent a little more time writing down the answers so I didn't have to work through it. So that means oxygen, we got 2, 8 plus 5 is 13. I need 13 oxygens on the other side. I'm just going to say, you know what? Screw it. I'm going to put 13 halves, also known as 13 double, double, and double. Then it's just a question of adding it all up, verifying it, and it should work. Okay. That's about it. Okay. The combustion reaction is one of the more difficult ones, particularly if you hit that weird kind of half fraction thing. You're like, well, how do I make a 13 an even number? That doesn't work. Okay. And that usually just involves dealing with fractions, which we're not allowed to have fractions. So you multiply it through by whatever your fraction is. It is typically a half, so you multiply everything by 2, and that kind of solves everything. Okay. Not a fun one, but that's why I told you to do it. Over 48 hours with office hours where you could have asked questions. Thank you. Double replacement reactions. Okay. Why did I say this could be written as no reaction? We didn't change the phase. The whole point of a chemical reaction is that we change phases, gases, solids, energy change. With no phase change, there's no chemical reaction. We can just write it as NR for no reaction instead of writing out the whole thing. Okay. How do we know it's no reaction, though? By typically writing it out and looking at your solubility rules and comparing it. So you typically have to solve it anyway. Go through and solve it as opposed to trying to do it in your head, because your head's a bad place to be. Okay? After that, what we'll move into is the PSS section on significant fig or sig-fig rules is the primary issue within this, but we'll define some measurements and then how we deal with sig-figs in scientific notation, and then potentially move into conversion factors. Okay? So, measurements. Measurements are always a number and a unit. Okay? I haven't railed about it at all yet this semester, but a number is meaningless. Okay? If I ask for an answer and you tell me 2, it's wrong. If I ask for my height and you tell me 6'4", that's wrong. 6 feet 4 inches would be correct. You need to specify those units. So what units can we use? Well, distance and length, what units do we typically use? Meters, miles, inches, feet. Okay? Depending on whether we're using the standard system or the American system, we use different measurements. Okay? Which is going to suck when we get to conversion factors, because it's then your responsibility to convert between them. And if we'd all just agreed at one system, you wouldn't have to convert as many of those nasty units. Instead, you have to deal with it. Okay? Our standards were created based off of the metric system. That is the standard system used for science, because scientists agree a little bit more than just the average human. Okay? It's Still not the greatest, but we get along a little bit better than that. Okay, so we have our metric system. Measurements are measured, or mass is measured using balances. Okay, so we're always comparing it back to something. What we're determining is the mass, not the weight, because weight is based off of gravity. Mass is an inherent feature of that material. They are kind of similar, and we tend to equate them. They're not the same thing. Okay? There's a neat little YouTube link there if you're interested in looking out at what a kilogram was defined as, because somebody thought it was really cool to come up with a better way to define a kilogram, and so that video is there for that. Volume measurements, graduated cylinders, also other things, okay, syringes. A lot of this is kind of in what you would see in the lab. They're just ways that we can measure volume. Why do we not measure mass when we're looking at liquids? If I pour a liquid out, what does it do? It just constantly moves. Okay? So I need to trap that liquid. It is easier to trap that liquid and measure the volume than it is to just pour it on a balance. Okay? It tends to ruin the balance. We get kind of upset about that. Okay? Now into the fun one, measurements with uncertainty. How long is that rod? The silver thing. Okay, it does officially say centimeters, so good call. I heard 4.22 centimeters. I heard 4 centimeters. 4.3, 4.23, 4.25. Of those, who is correct? Uh, 4.3 is the only one that is correct. Every other value is wrong. Yeah, it was like, well, what? Didn't we all measure the same thing? Yeah. That doesn't mean you use the device correctly. Right? What do all those numbers have in common? The 4. The instrument is precise to that place. Okay? Notice after that, we're getting all sorts of guesses. That's because the instrument is not precise to that place. We are guessing at that value. You are allowed 1 guess, decimal. That's it. Anything more than that, you are guessing upon a guess. That's bad. It's not good science. We can't do that. Okay? Why is the 4 on its own wrong?
Because it's obviously past 4.
We have a little bit more information about our measurement. We know it's past the 4. By just writing 4, we're ignoring that information. Okay? We can't ignore the information the device gives us. Okay? And this tends to kind of flip students out, largely because you don't experience this when you move into lab, because nobody nitpicks how you record your measurements. Typically also, when we go into lab and do measurements, we're usually measuring mass. How do we report the values of our sig figs from mass? This little device that we put stuff on spits out some numbers, and what do? You write down the numbers that it gave you. The instrument's doing the reading for you. Okay? Other devices, graduated cylinders, beakers, okay? Rulers, you have to do the interpretation. Okay? And that's why we have to be critical about how we observe our measurements and how we record them. So you get your absolute obvious digits, all of those need to get written, and then you get 1 extra guess. What if we want more information? Get a better ruler. Okay. What's better about this second ruler? It has more marks. Meaning I have 4, yes, but then I also know 0.2. Okay? And then I know I'm guessing somewhere after that 0.2. So I have a little bit more information because of the markings. If I don't have those markings, I can't make that guess. Make sense? Okay. The other fun part is uncertainty. Should always be reported with the measurement. You did uncertainty in the lab. What did you report your uncertainty as? How'd you get it? I was just curious. Maybe no one actually told you. Plus, minus, like 0.001. Is that familiar to anybody? No? Okay, let's not panic too much about it. Don't worry about it. We typically don't write it out. Okay? If you're going into some hardcore calculations, you would always report that uncertainty. It's very rarely actually supplied because it involves a whole lot more writing. And it's hard enough to get people to write on their own, much less adding a bunch of extra stuff that we wouldn't use. And we don't actually want to discuss. Okay? Which gets us to our sig figs. We take a look at those 5 values. How many significant digits are in those values? First one has 1 sig fig. Second one, that's a 1. That looks awful. Is that more like a 1? How about the next one? 2. Next one. 3. Next one. 2. Next one. 1. Okay. So we aren't perfect on it. That's okay. That's probably because you haven't worked through enough problems with significant digits. Okay. Remember, we had the video up there. You did it in lab. You may not have processed how it works. What's the issue here? Zeros. Was the 0 significant? Sometimes it was, sometimes it wasn't. And this comes back to what the 0 means. 0 can mean don't put a number there. 0 can mean there is no number there. And while that seems like a very subtle difference, it's huge as far as measurements and significant digits. Okay? When I look at that first number, that 0 is acting as a placeholder, telling me that I should not put the 1 in that location. Because if I put the 1 in that location, what's the number? 1 and not 10. When I move to the next number, that 0 is carrying an entirely new meaning. What is that meaning?
It could be more than 10. Just like pair more.
That the numerical value for the digit in the 1's place is 0. The numerical value for the second number, 10 or 1, 0 decimal point, the numerical value for the number in the 1's place is 0. For that very first number, what does that 0 mean? Don't put the 1 there. What numerical value could be in that 0 spot? Anything. It can be anywhere from 0 to 9. No, it's not 10. Okay? And this is one of the confusing things. You're used to looking at absolutes from mathematics. We write a number down, we say it's that many numbers. That's why we wrote the numbers down. Okay? That doesn't tie back to measurements. Okay? The measurements include those significant digits and what is important and what is not. Okay? And that's where this becomes challenging. Okay? If we were to measure something that said 100 grams, if we mass that, our balance is telling us that there's a 1 in the hundreds place, there's a 0 in the tens place, and I'm guessing that there's a 0 in the ones place. So we get that guess decimal. The balance tells me that. Okay? I don't know exactly what's happening in that last location, but this is a recording from the balance. When I record it from the balance includes that decimal point. But if I just say 100 grams, am I saying exactly 100 grams? Or am I saying about? Officially, I'm saying about. It's an implied about. What is about 100 grams? 99 is probably about. 101 is probably about. 105, probably about. 115, probably about. Okay? So when we're specifying our numbers, we must be very careful to not over-include information or remove information. And this comes from defining what are significant. Do not fail recording. This comes from what's happening within our significant digits. So we need to be able to define these and come up with rules for it. Our very first rule is an obvious one. All digits 1 through 9 are always significant. Okay? Notice I'm not mentioning 10, 11, 12, 13, 14, because what are those?
One and those.
Combination of the digits 1 through 9. Okay? So 1 through 9 are always significant. The challenge comes down to what is the 0. Is the 0 acting as a placeholder telling us that the significant digit should go somewhere else? Or is it acting as the value saying this means 0? There is nothing in this spot. Okay? And yeah, you're like, well, I don't understand that. Because we're saying it's nothing in one case and it's nothing in another. But they're different. Yes. Yes, we are saying that. I'm fully aware of that weird statement. Right? So how do we identify that? Your textbook and a bunch of others have gone through and listed like 6 different rules for significant digits. I would argue there's really 2. 1 through 9 are always significant, and 0 might be significant if now we have the 2 subrules. What I've got labeled here is 2 and 3. It's going to depend on the placement of the decimal point. If there is no decimal point, then for the 0 to be significant, it has to be controlled by other numbers. Right? And officially, not by other numbers, but by significant digits, which would be our examples of 1 through 9. Okay? To the left and to the right. At any place to the left and at any place to the right. Okay? Both of those conditions must be satisfied. If those conditions are satisfied, then the 0 becomes significant. If there is a decimal point, then a 0 needs to be immediately preceded by a significant digit to be significant, which means immediately to its left, I must have a significant digit. So, first example. Do we have a decimal point?
No.
Which rule do we need to follow?
The first one.
Okay. Rule number 2. So the 1 and 2, officially we had to follow rule number 1. But for the 0 to decide if it's significant, I have to have a 1 or a 9 to the left and to the right. So I'll start from my 0 and go to the left. What do I have? Is 1 a significant digit? Okay. Go to the right. Is 2 a significant digit? What does that mean 0 is? Significant, and I have 3 sig figs. How about the next number? 1 and 2 are significant. We'll take a look at the 0.
That was not.
That one's not. Why? There's no specified decimal point. So I have to look to the left. Do I have a significant digit? Yes. Do I have one to the right? No. Which means not significant. I only have 2 sig figs. You guys want to take a second to fill out the rest?
Please.
Okay. 1001. Let's move on. Next one has how many sig figs? 3 sig figs. The next one? 4 sig figs. I started, so we're going to come back and look at that. The next one, 0.12. 0.12. Next one. Also starred. Next one down. 3. And looks like we got that one. So let's go through and take a look at just the starred ones. Are we okay with that? Okay. And actually, before we do that, let's take a look at the purple. That's supposed to be a purple box. What's the difference between those numbers?
That's the 0 before the.
Just included the 0 in front. Why?
Didn't mess with this.
Why not?
It's a place.
What number? Let's try that again. What number did I write?
25.
No, I did not.
About 25.
What is that right there?
Oh, that's a decimal.
You can't see. It's not on the board.
What is the issue with decimal points? Particularly if you're using pencil, you can't see them. If I had instead written this, now you'd be like, why the hell did you write a 0 in front of 25? Oh, let's look really, really closely. There's a decimal point. Okay? It's called a leading 0. It's there to call attention to the decimal point. That's it. It has no significant value beyond that. It's just trying to make sure that if you're writing out a number, you don't accidentally turn that 0.12 into 12, because that's a pretty significant difference, believe it or not. Okay? So leading zeros, If you had me for lab, I complain about it all the time in lab. But you don't have me for lab, so you don't have to worry about that. Okay, so lower left hand. It was 4 sig figs. I heard a lot of people saying 3. So let's break it down. Underline, the 1 and the 2 are significant because rule number 1. Okay. Do we have a decimal point? Yes. So we're moving to rule number 3. The 0 needs to be preceded by a significant digit. So that first 0 that I see, what is to its left? A significant digit, which makes that 0 significant. Okay, we'll move to the next 0. We look to its left. What do we see? A significant digit, which makes it significant. There's 4. What's that? If I continue to write zeros, yes, I could go on forever like that. Right? I could have 1,000 significant digits. Yes. Right. Next one. Yeah, I think we had problems with that. So underline the important significant figs, 1 and 2. Okay. For 0 to be significant, what has to happen if there's a decimal point? Preceded by, to the left. What is to the left of the first 0? Nothing. Which means not significant. What is to the left of the second 0? A 0 that was not significant, which means it is also not a significant digit. We only get 2 sig figs. 3 rules. Not this nonsense of 20 rules. I think actually a faculty member was like, oh yeah, it's you and your OChem stuff making it so much simpler. It's not that much simpler. You're full of crap. Yeah, it is. There's only 3 rules. There's not this 20 rules and, oh, it's ambiguous. No, it's not ambiguous. It is this. You're just confusing people by calling it ambiguous. Okay? Fix your notation. Okay? And that's coming from somebody that doesn't like numbers. If you like numbers, you better understand it. Okay? Man, I'm getting awfully riled up today. I started yelling this morning too.
It's because you don't feel good.
I don't know, maybe it is. So let's move on to the next one. This is a good one. Measurement versus exact. How many quarters? What's that?
We can go over the last one.
Oh, did we need to go over the last one? Sorry.
I felt like I needed to.
Okay, no, that's cool. 1 and the 2 are significant.
Yeah.
With a decimal point, we look to the left. Is the 0 significant? First 0. No. Next 0. Last 0.
Yes, because of the
Yes, because of the 2. We get 3 sig figs.
Cool. Thank you.
You're welcome. Measurements. How many quarters do you see in that picture? 7. Let's write that down. Ready for this? 7 quarters. That says quarters. Trust me. I'm a chemist. That doesn't end well. How many sig figs?
none, because it's possible.
I don't accept none. 1. I'm hearing 1, right? 7 is a significant digit. That's between 1 and 9, right? So I hear 1 as a significant digit. Hearing none. None does not count because 7 is, by definition, a significant digit. So we can't have no significant digits.
Right, I was just thinking plus 1.
For those of you saying none, what is your other limit?
7.
There is an infinite amount of significant digits in this. There's not 7.1 quarters, there's 7 quarters. So you can fit, well, then it's 7.0 quarter. Well, then is it 7.01 quarters? No, so it's 7.00 quarters. 7.001 quarters? No, 7.0000 quarters. 7.000001 quarters? Okay. We have an infinite number of sig figs. Okay, which gets back to your question about 1,000. Typically, if we're looking at our numbers, if we're going to hit lots of sig figs, it's because it's an exact value. 7 quarters. Okay? Other examples where this shows up. Okay, here we go. How many inches is this? How, 12 inches is?
Foot.
1 foot. How many sig figs in the measurement or the calculation 12 inches is equal to 1 foot? It is infinite. There are exactly 12 inches in 1 foot. It is not 1 sig fig because of 1 foot. It is not 2 sig figs because of 12 inches. They are exactly 12 inches. This is a defined value. As soon as we define something, then by definition, using definition and define in the same statement, okay, it is an infinite amount of sig figs. Believe it or not, it isn't that tricky. Okay? Because where you'll be seeing it is with big conversions that you're used to. Okay? 12 inches is 1 foot. Okay? How many ones are there in 10? That may have been a bad example. Don't ignore me. I mean ignore me, don't not ignore me. So the amount of quarters is a good example. So we have to watch out for exact measurements. They're not typically measurements. What they are definitions. Okay? Counting things is an exact value. Okay? The number of people in this classroom, we're not going to have fractional people. Okay? We have an exact value of people. Kind of make sense? Okay. So why do we care about sig figs? Okay? What does the calculator tell you the answer is to this question? Well, using my long arithmetic skills, 1, 1, 5, 1, 3, 2. Yeah. Rams. Because I'm awesome at addition. Okay. If I ask you that on a test and that's the answer you give me, or actually that's the answer you bubble in on the multiple choice, you are wrong. Because of sig figs. When we're doing addition and subtraction, our answer can only be as precise as the least precise measurement. If these are all measurements, when I add them up, okay, I have to take into consideration the precision of those. Which of those values is the least precise? The 14.3 is the least precise. Why is that less precise? I know information all the way up to what place? The tenths place. What do I know about the next number? Tenths, hundredths, thousandths place. I have more precision. The next number, I'm not even going to try and say what that one is. Okay? We have a lot more precision the further out we go, which means the answer can only get reported to the hundredths or tenths place, which then means I go down here. That's my last value. My answer must be this, 115.6. What happens to the 3362? Disappears. The only thing we'd ever be concerned about is potentially rounding up. We'll see that in just a little bit. That's I carefully picked this. Okay? And for people saying, well, I don't believe that that makes much of a difference. What is this number right here in that space? I don't know. Literally, I have no clue. That's why I didn't write a number there. I don't know what it is. Which means it could be 0, and it could be 9. How about the next number? Same issue. So what happens is we scale this out. What our calculator does is we're immediately saying the rest of those numbers are zeros. We are adding information that we do not have. Those could be zeros, those could be 9s. How does that change the number? Well, in the bottom case, because again, that whole arithmetic, I'm awesome at it, 115.7346, versus what we had before, 115.63362. Is that a significant difference? Yeah, we went from 0.6 to 0.7. Okay? That is a significant difference. A tenth of a value, believe it or not, can mean life and death. Okay? So we have to be very, very careful that when we do addition and subtraction, we don't start adding in more information than we have. Okay? So it has to go back to the least precise place. Okay? Question? Okay. Are there other mathematical operations we can do? Yeah, like multiplication and division. Well, what's our rule with multiplication and division? The result is only as precise as the measurement with the fewest significant digits. Wait, isn't that what I just said?
No, because you said what's just the least precise with the decimal.
One says least precise, the other one says
The amount of significant.
the number of significant digits. Okay, and so, well, again, what's our difference? We have 2 sig figs versus 3. When I go through to do the multiplication for the area of the square, 7.28 units times 4.6 units, our calculator spits out this value. How much of that value do I actually know?
48.
I can only go to
Oh, that's
2 sig figs. Not the tenths place, 2 sig figs. We're 2 sig figs in the number 33.488. Just 33. And my answer is now 33 units squared. And again, people then go, well, didn't we lose information by ignoring that 488? No, we're not allowing ourselves to overanalyze. Because again, I don't know what that next value could be. I'm assuming it's a 0. Okay? It could have been a 9. Okay? It does make a difference. We go from 33 to 34.
Could you explain that again as far as why we knocked out the 48?
Because our rule for multiplication division is fewest number of sig figs. When we look at our calculation, the first number, 7.28, has how many sig figs? 3. 4.6 has 2. Which has fewer, 2 or 3?
4.6, 2.
So 2, which means my answer can only get reported to 2 sig figs. 33 is my answer.
All right.
Okay. Believe it or not, you will only remember one of these 2 rules. Any ideas which rule you're going to remember? Addition, subtraction, or multiplication, division? Multiplication, division, because nearly everything we do is multiplication, division. Very rarely do we do addition and subtraction. Okay? So that means addition, subtraction almost invariably shows up on the final because everybody has decided to forget that they need to know it. Just so you know. Okay? Yeah. I'm very subtle. When rounding, what have we changed our numbers? In our addition, subtraction, this answer, where should I be reporting to? I can only go to the hundredths place, so those are the values I'm allowed to keep. What's the issue? I'm now starting to get kind of darn close to it being 0.0 or 34. Okay? So we need to decide, when should I round that up? When should I leave it alone? Kind of arbitrary, believe it or not. Most people seem to be following this rule. If your first non-significant digit is less than 5, leave the number alone. Okay? If it is 5 or larger, add 1. Meaning, our answer for our addition, 1, 2, 3, we are greater than or equal to 5, which means what do I have to do to the previous digit? Add 1, and my answer becomes 1.34, and we would be wrong because we didn't write the unit. Okay? What about the next one? 7.8 units squared, or 7.8 units times 4.68 units. How many sig figs am I allowed to keep? 2. So I'm allowed to keep the 3 and the 6. What's the issue? That next insignificant digit is 5 or larger. I need to add 1 to the previous digit, and this becomes 37 units squared. Already catching on fast with the units. Good job. Okay? So you're saying, man, I'm going to need some practice with this. Yes, you probably will. That's why you should do it. Okay? How much does this actually impact us? Okay, and this is actually going to be a nice little pause here. So, you want to do a little bit of practice? I didn't hear anything kind of excited about that, so we'll go ahead and move on. We put it all onto one side. Sigfigs. We got our rules for our sigfigs up at the top. Our rules for addition, subtraction. Our rules for multiplication, division, and then rounding. It's now all on one beautiful slide. Feel free to take pictures if you would like. But it is in the PowerPoints. All you got to do is, download the PowerPoints. Yeah. Seriously. Who would download PowerPoints? I mean, it's not like the person that built them spent a lot of time trying to help and give you feedback so you learn more or anything. What was that? So, some mathematic simplifications. Okay. Write 4 times 4 times 4 times 4 times 4 times 4 in your notes. I don't see anybody writing. No, I'm serious. Write it out. You got a calculator? Do it again. Enter it into the calculator.
You want us to write the long word?
Anybody go that sucks. Why are you making me do that? That's stupid. Yeah, it's because it is stupid. We come up with simplifications, right? Okay, why do we come up with those simplifications? Yeah. See, it's part of that anger thing. You help remember. Okay. We simplify this down to 4 to the 6. We can use an exponential value. Why do we go through and do that? It's easier. I already saw half dozen. 1, 2, 3, 4, 5, 6 4s. Okay, yeah. What happens if you miss? Your number all of a sudden changes and you get the wrong thing. So we switch to exponents to simplify things and condense them down. You can do the same thing on your calculator. If you need help finding that button on your calculator, talk to me. The EXP tends to be a standard one. X caret to the Y also seems to help. Okay? You may want to use that for your doing calculations. Okay? Some common ones that pop up, squared and cubed, ultimately coming from if we have one dimension, we have one dimension is a line. What happens if we have 2 dimensions? We have a square, we have a length and a height. So what's squared coming from? Length times height. What happens if we add a 3rd dimension? Okay, we end up with a cubed. Okay? So our squared and cubed terms are referring to how many times we're multiplying a unit out. Squared means we're multiplying twice. Cubed means 3 times. Another big summary one here, powers of 10. Okay? We can use our exponents to scale up really big numbers, okay? Or really, really small numbers. And everybody goes, well, it's not that hard for me to write just 10. Why do I need to write 10 to the 1? You're right. You could probably just get away saying 10. But what if you had 1 million? It's a lot of zeros. Is it easier to say 10 to the 6? Yeah. Okay. So what we'll do is scale and use that information when we move into conversions. Okay? Or, before we even get to that, scientific notation. Okay? We can take really big numbers, and instead of writing them out as these big, long things, I can abbreviate them down into a scientific notation. So our rule, or steps for this, step 1, place a decimal after your first significant digit, and then follow it with the remaining significant digits. Okay? Indicate how many places you moved your decimal by using your n factor, which is the bottom one. Okay? If your new decimal is to the left of the... actually, I don't like that one. I keep forgetting to change that. So I'm going to erase that real quickly. Largely because I'm not even sure if that's right. And there we go. Take a look at an example. The first number, distance between the Earth and the Moon. Our first significant digit is 4. We'll follow it with the rest of our digits. Our decimal point is 0, 6, 3. The other zeros are not significant because no decimal point. I will then do times 10. Okay, how many times did I shift the decimal? So I started from here, a phantom decimal, 1, 2, 3, 4, 5, 6, 7, 8 times. Okay. Was the number really, really big to begin with? Then your n value is positive. So I shifted it 8 places. It's a positive 8 because my number was big. How about the next one down? I was just testing you. Meters. Next one, 1.16 times 10 to the, how far did we shift? 1, 2, 3, 4, 5, 6, 7. Whoever's shouting out that 8 and 7 and can count that fast, that's not nice. Was that a bigger number or a smaller number? I'm looking at a small number, so it's got to be negative. I am kind of kidding. You're fine to shout that out. It just makes me look like an idiot. Okay? And for those who think, isn't it kind of silly to show this little circle thing? Is anybody actually using one of the borrowed calculators from the school?
No.
If you look really carefully at most of those screens, you'll see these stupid little curls. It's actually kind of funny because people are counting them out, getting this down. Okay? So I would recommend you do this little shift thing. Okay? I think it works. Moving backward, I don't want to even open that up.
No?
Okay? So that's our scientific notation. Why else do we actually use this? It's not just I can get rid of a whole bunch of stuff that I don't have to write it all out. But what happens if I want to measure the distance to the moon as follows? How many sig figs in each measurement? And actually, I'm going to do one little cheat here. Get rid of that because that's just annoying. So on the top one, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. That would suck to write scientific notation because we got the 4.06,
Why is it?
3, 0, 0, 0, 0, 0 times 10 to the, what do we say, 8? 9? I totally thought it was 8. 1, 2, 3, 4, 5, 6, 7. It's 8.
The 4 is not a significant leap.
Oh, counting sig figs. Sorry, I see what you're saying.
Yes.
Okay. How about the next one down? 406 million. How do I convert that to scientific notation? 4.06 10 to the, still going to be 8 because it's still a million. Okay. How many sig figs in each of those measurements? We had 9 in the first one. We had 3 in the next one, right? Okay. Somebody came through, took that 406, said it was 406 million, and it was exactly 300,000. Meaning the 4 is significant, the 0 is significant, the 6 is significant, the 3 is significant, and I know for a fact that those zeros are not 1 through 9, that they are actually zeros. Write this number in a scientific notation. Well, 4.06300 times 10 to the 8, right? How many sig figs in this measurement? 4. But didn't I say that this is the proper interpretation of that? Because I said that those zeros were significant. When I write out the full number, How do I know those zeros are significant? Okay, what happens if you drop a decimal so that you can make those zeros significant? Well, now it's not 400 million. Drop it at the end. What happened to these zeros now? They became significant. I said those weren't significant. How can we run or fix this issue? The only way you fix it, scientific notation. Scientific notation completely unambiguously removes our issues dealing with zeros acting as placeholders or acting as numerical values. Right? Because scientific notation always includes a decimal point. Whereas an actual measurement may or may not include the decimal point. So scientific notation is the be-all, end-all for keeping proper track of our sig figs. Right? That can simplify things kind of nicely. Ignore that comment to Greg. Okay, chapter 2, our metric system. Okay. Number one thing to realize is that our metric or all measurement systems are an arbitrary human invention. Okay? This wasn't then just stamped from on high, whoa, 12 feet is 1 inch. No, some jerk-off said, well, on my inch, my thumb is roughly 12 of them in my foot. Everybody listens to me now. This is our measurement. What happened when that guy died? The next jerk-off said, well, my thumb is now the standard measurement. Everybody has to measure me. Okay? That's a really stupid way to measure things. Because whenever somebody dies, you have to reinvent the wheel. Okay? So we had to come up with standardized systems. Okay? The standard system for metric, length we measure using meters. Mass, technically it's kilograms, not grams. But what we're listing here are what I'd like to refer to as the core unit. Okay? So our core unit will be meters for length, mass is gram, liters is volume, and time as in seconds. Okay? The reason we list these as our core units is that we can then scale these to different sizes using powers of 10. Okay? For instance, kilogram, which is by definition our standard unit. Okay? What is a kilogram? Well, the abbreviation for kilogram is kg. What is K equal to according to this little chart? 1 times K was 10 to the third grams. Guess what we now have? A conversion factor that relates kilograms to grams. Okay? The Greek prefix sets us up with the conversion factor. Some of you may have gone through and said, well, it's 1,000 grams. Yeah. What is 1 times 10 to the third? 1,000. Okay? So what you should go through and do is memorize your Greek prefixes and what they mean as far as powers of 10. Okay? That's not bad. That's only like 10 more things. You're not saturated yet, right? Jam some more stuff in there. Narrow it down to 3. Kilo, memorize. Centi, memorize. Milli, memorize. Why those 3 and none of the others for memorization? Those are going to be the most common ones you'll use. Deci does show up, micro does show up, nano does show up. I don't think I've ever seen mega, giga, well, technically megabyte, gigabyte, terabyte, but in chemistry, we don't deal with that. Okay? The deci, micro, nano, and pico do occasionally show up, but those are showing up typically as a way of kind of like sticking it to students. Ah, you didn't memorize that one. Okay? When it comes to a test, if I ask you about nano, pico, or micro, guess what else I'm going to give you? That conversion factor. I'll tell you that pico means 10 to the negative 12. Okay? Where will I tell you that? Might be in the question, but it'll probably be on the very first page. This is why it's helpful to tear that first page off. You now have access to that information quickly and easily. Make sense? Do you want to set up some conversions here? Okay. I'll do the first one for you. Okay. Scientific notation. I have 1.2 times 10 to the, I went 1, 2, 3 locations, 10 to the third. Since 1200 is a big number, that's going to be a positive value. So 1.2 times 10 to the third meters. What is my number in new unit? Well, my number is going to be 1.2, and my new unit will be 10 to the third times meters is kilometers. So we are all human. So we go through and shift our decimal. See, now that we're recording, see, everything's lovely. We went 1, 2 locations to get to 1.2. So we shifted it 2 places, so that's 10 to the second. But it's a small value, so it'll be negative second and seconds. The next one was also by 2 liters. And the next one, 3 and negative 3 and grams. And I will acknowledge, you were correct. Thank you for calling that out.
What did he say?
That I was being an idiot, and that's why I erased some stuff. Said it a little bit nicer than that. 10 to the minus 2 is defined as centi, so I end up having centiseconds. 10 to the minus 2 is defined as centi, so I end up with centiliters. 10 to the minus 3 is defined as milligrams. There it is. Sweet. Okay. Sure. We get some translational stuff coming out here. There are 1,000 meters in 1 kilometer. Okay. Mathematically, that means 1 kilometer equals 1 km equals 1,000 meters. Can we convert that into a fractional notation? Okay, so let's just take a look at that last little part. What happens if I divide both sides by 1 over km? What does the left-hand side of the equation become? 1. And the right-hand side? 1,000 meters over 1 kilometer. What I've now generated is a fractional notation. I can now show a relationship between 1,000 meters and 1 kilometer. Did I have to divide both sides by kilometers? Nope. I could have done it the other direction. So I have 2 formats when I'm looking at an inequality for generating fractional notations. Those fractional notations are now conversion factors that I can then use to convert different units. In particular, in this case, converting meters and kilometers. Okay? So it's just recognizing that that is true. That's all I want you to get out of that. Okay? So yeah, ignore all that. Yeah. We're going to ignore the mathematical manipulations. No one seems to like that. So let's move to converting a process. Oh man, my nice conversion question isn't there anymore. Did you say ha ha ha? Okay, so I'll just have to come up with my conversion question. This is a difficult one, so I do suggest you take your time working on this. How many inches in, you guys ready? 3 feet. Now don't shout out, I mean, people are still working. Okay? And what I care about is your work. Okay, you want to share with the person next to you? What did you get for an answer? Don't put it in scientific notation. That's a bit excessive, but we could do that. What do we get? 36 inches. Okay. Remember, I want work. What did you do to get 36 inches? Thank you, Jerry, for shouting that out. I needed that. 12 times 3. 12 times 3 equals 36 inches. I don't think so. That's not true.
12 inches or 3 feet.
Because if I look at that right, inches didn't show up on the left-hand side of the equation. That's not an equality, so that's not right.
1 foot equals 12 inches.
1 foot equals 12 inches, and that equals 36 inches. No, okay. 12 inches over 1 foot times 3 feet. Your units cancel, and now 12 times 3 equals 36, and the unit left over would be inches. And you might be saying, well, isn't that kind of dumb? Couldn't I have just done that on my own? Yes. The conversions we are launching to in this unit, or the tail end of this section, are all dumb conversions that you could do in your head. However, what happens if I mess with you and change the unit to something you have no concept how to manipulate or understand?
Then you won't know how to do it.
Then you won't know how to do it. So the point of this section is not to get 36 inches. The point of this section is to get your work correct. Right? I cannot stress that enough, because everybody looks at me like, this is a dumb calculation. I didn't have to do this. You're right. It is a dumb calculation. But the instant I change it into moles, you screw it up. Okay? So make sure you set up your equalities. Always set up where you track with your units. The unit tells you how to solve this. This wasn't 12 times 3. This was saying I have inches as a final answer. That's what I want to get to. Which means on the left-hand side, I need inches. Do I know anything about inches from the question? I'm expected to know that there are 12 inches equal in 1 foot. I've now brought in my 12 inches, or my inches unit. That's awesome. But what did I also bring in? Feet. Feet doesn't show up in the answer, so what has to happen? I need that unit to cancel. Am I given a numerical value associated with that unit of feet? Yes. Now I can bring the numerical value in. Now I can run the calculation. Yes, that will slow you down now for massive gains later. Don't believe me, fail the next exam. That's fine. That's your call. Okay? Work on setting up the conversions. Get your units set up. Track your units. We will pick up there on Tuesday. The exam is Thursday. Most of what we will be doing on Tuesday is practicing conversion factors. That's all it is.